So, right, so like we were saying, you can either find out what all seven of these probabilities are and add them up, or just find this one and subtract from one, and because these are all different, right? They're not all equally likely, so it's a lot harder to calculate all seven of them and add them than it is just to calculate this one and subtract it from one. So you guys are asking great questions.
Thank you.
Yeah. Thank you. I'm going to skip this part here. Okay, so this one is something that we need to cover. So say we're choosing appetizers. You're throwing a party. And they say, okay, well, you can choose 3 out of 6 of these appetizers to serve at your party. So that is kind of your number of appetizer combinations you can pick. Right? I can pick these 3, I can pick those 3, I can pick those 3, those 3. So all the other, there's like 20 different possibilities of appetizer combos that I can choose. Right? I can go wings and shrimp balls, crab cakes, right? Or I can go little hot dogs and shrimp balls and chips, right? But anyway, so there's 20 different ways you can pick. You can have 6 different entrees and choose 3 of them. So there's 20 different possible kind of entree combos. And then you get to pick, from these 5 entrees, you get to pick 3 that you can offer to your guests. So yeah, kind of snazzy, right? So how many ways can you pick 3 different entrees out of 5? 5 choose 3, which happens to be 10. So it's 10 different ways of picking kind of entree combos. How many ways are there of having a meal altogether? Well, I have 20 of these, right? And I have 10 of those. So every 20 of these, I have 10 different possibilities for the entrees. Right? So this would be 10, sorry, that's wrong. 20, I'll give you the thing first. It's 6 choose 3, and this is 5 choose 3. So this is going to be 20 possibilities there. And for every one of the 20 possibilities, I have 10 entree combinations, right? So if I picked shrimp and crab cakes and escargot. I think they're going to be escargot. There's no way. Okay, shrimp, crab cakes, and hot dogs in a bun. Then I would still have 10 different entree options I could choose from. But if I choose shrimp and crab cakes and chips, then to have another 10, entree options to choose from. So for every one of these 20, I have 10 of these options to pick from. So I have 20 times 10 total possible menus I can choose from, right? Because these are how many options I can pick from the appetizers, right? My number of. I have one decision to make here. I have 20 choices. I have another decision to make here. I have 10 choices. So fundamental accounting principle, 20 times 10, I have a total of 200 outcomes. Wow. It took me literally 2 classes before I finally got that explanation nice and clear. Thank God you guys are in the 7:30 class. Okay. All right. What if you also have to choose 2 out of 4 desserts? 5 choose 3. What would be then what would I do here? Help me out, guys. No? 4 choose 2. So maybe the longer way was easier. So what I did there was, okay, so imagine, right, there are, I don't have any boys and clusters of boys and girls sitting together. All right, we'll do it this way. Left side and right side. So there's these 6 people on the right side of the room. Right? I can pick any 3 from this 6. How many ways can I pick 3 from the right? I can pick those 3, or these 3, or those 3, or those 2 and these 3. Right? There's a whole bunch of those 20 different ways I can pick 3 of them. For every way I can pick 3 of them, I can pick from this side of the room. I can pick 3. These 5, I can pick 3 students here. So if I pick, how many ways can I pick 3? I can pick these 3, or those 3, or those 3, or those 3, right? So for every way that I can pick 3 of these 6, I have 5 choose 3 ways of picking from this side of the room. Right? So I have 6 choose 3 times 5 choose 3 ways of total of getting 3 students out of this group and 3 students out of that group. So now we add in another layer, we have dessert options, right? So we have people in the back row. How many ways are there picking 2 out of 4 of them? Times 4 choose 2. Makes sense? Just kind of goes on and on. So this is like my appetizers. I have 20 different ways of choosing an appetizer group, right? And from every one of those appetizers, I have 5 choose 3 ways of picking an entree. So how many groups of these do I have? If I have 10 of these, I have 20 groups of that 10. If I added in desserts, then off of each one of these, I'd have a whole bunch more 4 choose 2 of those. Good? All right. Cool. All right. All right. You're not getting tested on it, but I did need to show it to you. All right. So next thing is what counting methods. So I want to make sure you guys are super clear on which counting method to use. So first of all, counting is whenever I say how many ways, that's going to be counting principle. That's counting the counting stuff in 4.4. Excuse me. So first of all, it's with replacement. So you can reuse items. Or if the items are in totally different categories, like you're picking pants and shirts and socks, then it's just regular fundamental counting principle. Right, so it's like the shirts and socks and the pants and the shoes, remember that one in the beginning? Or the car, right, the exterior, interior color and the engines and stuff like that. If it's without replacement, so in other words, you have a whole pool of items you're picking from, one pool that you're choosing from, and when you pick from that pool, you cannot reuse items. So I'm picking 3 students. Once I pick a student, I can't pick the same student again. Then it's permutation or combination. If it's order matters, it's a permutation. If order doesn't matter, if they're all kind of rolling around in there wherever they want, then it's chaos. It's a combination. And that's when you have to divide out the duplicates. That extra step. This one requires the extra step. That's the only one that does. That chaos thing. Because it's craziness. You got to do extra steps. You got to divide stuff out. Don't worry about the last part. I think we're going to not focus on that. That's basically what we just did a second ago. Summary. Okay, before we get to that, I brought in some chocolate truffles. I don't have a lot though. So we're going to do this way. If you want one, come on up. We'll take like 5 or 6 people if they want to try first. And then we'll take another 5 or 6. So let's get the first 5 or 6 up here. If you draw a red card, you get a truffle. If you don't, then you don't. So you got to take your chance. You can pick anyone on the card. So let's get 5 or 6 people up here first to try. 1, 2, 3. 2 more can come. 1 more. Oh, there we go. We're full.
I saw 4 of them.
Go big or home.
All right. Yep. So you can draw anywhere from anywhere on the deck. Draw a card. Show it. All right. Lose. Go back. Try. It's first. Pick anywhere you want. Pick the same exact card. Okay. Right.
No.
Next, go ahead. Draw. All right. One more person. Go ahead and draw. Anybody else want to draw? All right. One more person. Oh, 2 more people. Come up. Go ahead. Both of you guys. Go. Good. Ace. All right. So
The game's jinxed.
So there's some theory, right, that sounds like some of you guys think that my deck might be a trick deck, maybe. So the question is, we're going to talk about hypothesis tests just for a minute. This is a preview of what's coming in chapter 8. So the null hypothesis says, null zero hypothesis says that my deck is the same as everybody else's deck. That's always getting the null hypothesis. Yours is the same as everybody else's. So if my deck is the same as everybody else's, what proportion of black cards are there? In a regular deck, what's the proportion of black cards?
26 to 1 to 2.
1 to 2. Half. 50%.
Yeah.
Make sense? So proportion would be 1/2 or 50%. So then we took a sample. We had 6 people draw. Is that right? So the first person, what's the probability the first person gets a black card? 1/2. We put the card back, so what's the probability the second person draws a black card? It should do the exact same card. What's probably the next person gets half? The next person? The next person? The next person? Now, what's probably the first person and the second person and the third and the fourth and the fifth and the sixth all get a black card. And we multiply. So we're going to multiply these. And we end up getting 1/64, which I think we talked about last class was 1.6%. What's our guideline for unusual?
Under 5.
Yeah, 5% or less. Is this unusual?
Yeah.
Guys, is this unusual?
Yeah.
Yes. So this is unusual. So what is more likely, do you think, that we just happen to have gotten unlucky? These 6 people got unlucky and they all drew a black card. Or do you think it's more likely that my deck is fixed? It's more likely it's fixed. Do you see what I'm saying? So it's possible. Is it possible that they all just got unlucky?
Yeah.
Yeah, it's possible, right? 1.6% of the time that's going to happen. And if you go down to the casino down the road where I used to deal at, you will see on the board, it shows you banker and player, roughly 50%, you will see strings, at least one board will have a string of 6 or 7 of all banker or all player on it. Guaranteed, at any point in time. It happens, right? I mean, at some point during the night, there'll be a string of like 8 or 9 that are all banker or all player, at some point, because there's 7 tables going, tens of thousands of hands going a night. So it's possible, but it's more likely that my deck is fixed. So we would, in this case, what we do is we make a hypothesis that our deck is the same as everybody else's. And then we take a sample. If our sample is unusual, then we say that our deck is not the same as everybody else's, and we reject the null hypothesis. So I should do that in marker, yellow marker. Reject the null hypothesis. So that's the idea. If, again, null hypothesis is that your deck is the same as everybody else's. You take a sample. If your sample is unusual, then you say that my deck's not the same as everybody else's. Your deck is fixed. It's somehow different. So does that kind of make sense to folks? That we got something unusual, so my deck is probably not half black cards. I mean, half. It's probably not half black. It's probably something higher than half. Maybe all. Who knows? But a lot. Possibly. It could be. It could be not.
Was it?
I don't know. Who knows? It might. It seems like it's probably not a regular deck. It seems like there's really good evidence that it's a fixed deck. We can't know for sure because there's that statistics. There's all this uncertainty, right? It's all about randomness, and it's hard to be certain of anything. But it surely is good evidence, very good evidence that it's a fixed deck.
What did the other classes get?
Huh?
What did the other classes get?
Oh, I'm sure they got all red cards. All right, let's get back to our summary. So I'm just going to quickly summarize some of the main parts about the probability for you guys. The first one is and means multiply. Make sure you say that to yourself 5 times every day for the next 5 days. How do you So just as a visual for that, is if you look at heads and tails, there's a half chance of getting tails, right? And if I want to get tails, probably I get tails and I roll a 4. There's a 1/6 chance of rolling a 4. So there is this amount is rolling a 4 and getting a tails, doing both of them. So it's 1 out of 12, right? So it's 1/2 times 1/6, 1/12. So again, and you multiply. Don't forget that if it's dependent, you have to multiply by the probability of A times the probability of B given A has happened. So if it's dependent, you have to add that given part. Or means add, then subtract the overlap. And you know what? Are you guys okay if I go back one for a second? I want to talk about this real quickly.
Anything to support you.
I think it's coming up in the next. Actually, it's coming up in the next one. That's okay. Actually, no, it's not. All right. So yeah, it is. I'll do it later. All right. So then, or means add and subtract the overlap, right? So what's probably I get a tails or I roll a 4 when I do both of these things together. So 50% chance I get tails. 6 out of 12 chance I get tails. 2 out of 12 chance that I roll a 4. So 6 out of 12 plus 2 out of 12, but I have to subtract the overlap. 1 out of 12. So it's really only 6, 7 out of 12. So you add the probabilities and you subtract the overlap. And then the other thing that's really important, which we talked about a lot today, was if you want to find the probability of at least one, either I have at least one sibling or I have no siblings, none siblings. Right, so those are complements. So you can either find all of these and add them up, or just find this one guy and subtract from 1, because all of them have to add up to 1 or 100%. Okay, I do want to talk about dependent and, did I not say that anywhere in here? Oh, yeah, it is in here. Okay. Independent. So mutually exclusive. Remember, that's when they have, mutually exclusive has no overlap. You cannot be both at the same time. And if they're mutually exclusive, you just add them. If they're not mutually exclusive, you add them and you subtract their overlap. I think you guys are all right with that part. The other thing that I think people get confused about is this whole independent thing. How do I know if male and brown are independent? There's 2 ways that we talked about figuring that out. One is figure out the browns and the males. So male, brown, male, and the total, and find the ratios. So is 5 out of 6 equal to 19 out of 30? It's not equal to, so it's dependent. Everybody on board with that part? Now, as someone pointed out, you could look at it the sideways way and say, is 5 out of 19 the same as 6 out of 30? And that also works. The second way you can do it is you could say, does probability of brown and male equal the probability of brown times the probability of male? So what's probably that you pick a, the puppies are supposed to be, that's right, the chocolate lab that's male, 5 out of 30. Is that equal to the probability that it's an all brown puppy, and they're solid colored puppies, all right, just work with me here. 6 out of 30 times 19 out of 30, are those equal? No, they're totally not equal. So since they're not equal, then again, this is dependent. Okay? All good? So those are the 2 ways of testing if something is independent or not. You can just look at the ratios, or you can look at the probability of both equals probability of one times probability of the other. That's okay. So we'll skip these. All right, so I think the rest of them are not as critical. Well, yeah, this is actually kind of important too. Multiple events. So remember, if you're not replacing, then all of a sudden it changes, right? Red then blue. 2 out of 12 are red, but then now you have 1 less marble. So the blue one, you still have 6 blue ones. That's okay. But if you're talking about 2 blue ones, 6 out of 12 are blue. But then for the second draw, only 5 out of 11 are blue. Because there's 1 less marble and there's 1 less blue one. Everybody all right with those 2 things?
Yeah.
All right, so I'll leave that up there, and you guys do problems 1, 2, and 3. Try doing 4 too, but let's get 1, 2, and 3 knocked out in the next. Problem 1, do not spend more than 5 minutes on it. And then we're going to move on. And then we'll go over them.